Hi, thank you for watching this video. It's been a while since I made last video. It's been 7 months to be precise. I've been learning about something called GAN, Generative Adversarial Network. Very, very interesting concept and topic. Something which can generate the data. Okay? So, it was so interesting that I thought that let me share this knowledge with everybody else. In order to share that knowledge with everybody else, I realized I have to basically explain about how neural networks work, because the working of a typical GAN is based upon a neural network, and hence this is the first video in the series of neural networks which I will be more I'll be uploading more videos and more often now, uh, to explain the neural networks and eventually going over to GAN. So the video series will basically start from a very basic, and then gradually it goes towards complex functioning of a neural network and eventually to the GANs. So that's what my aim is. If I'm able to finish all those video series. So I have this notebook with me, which I basically used Google Colab and developed this entire notebook, and then I downloaded it in my system. Right? So this basically explains the working of a single neuron. This is where we start from. So in this video series, this is what I intend to do. First, explain about single neuron. Then I explain about network with multiple neurons. Then I explain about network with multiple neurons plus multiple layers. So this concludes our neural networks, post which I move on to GANs. Using GANs, we generate data. When we generate data, we are talking about something like an entire picture being made by a machine, an entire music, or an entire song being made by a machine, a movie which is made by a machine, instead of a human behind it. So somewhere down the line, it also links to emotions. Right? So opportunities are endless. Yeah. So before we move on to all those complex things, let's get back to understanding the basics. A single neuron. Okay. So how does a neuron look like? This is a neuron. Just one moment. I'm not too good at drawings. Yeah. So this is the basic working of a single neuron. X1 and X2 are the data points which are being fed into the neurons, right? Yeah. So based on X1 and X2, Z is calculated. Z is further converted into A, and then we get the prediction. Y hat, I call this as Y hat. Y hat is nothing but the prediction, which is made by this neuron. Now, let me explain you further what is happening here. Right? So these are weights, W1 and W2. So Z is basically equal to dot product of weight and X added to, which is added with a bias. So we have Z1 and Z2, which is X2, dot product of X2 and W2, plus added to a bias. Okay. So this is what is happening in the first part of the neuron. And then we come over to the next part of neuron, which is the A. So how do we calculate A is nothing but a function applied to Z. In this case, we are going to use sigmoid. Just one moment, please. So in this case, the function f is equal to sigmoid. In practice, we don't use sigmoid so often unless we are talking about a binary classification. We don't use sigmoid in practice. Sigmoid layer is being used as the output layer only in case when we are doing a binary classification. Otherwise, we go for different types of functions. I will be explaining these activation functions in depth in the next video. However, in this case, for demonstration purpose, I'll be using a sigmoid. Okay, so this, so based on this, and once we apply this activation function, we get A. This A is nothing but the output, the prediction, which is done by the neuron. So this is part one. This is the first part of just one minute. Yeah. So this is called forward propagation. This is part one. Then we have a part two, which is called backward propagation. Okay. So this entire explanation which I gave is basically for forward propagation. In backward propagation, we basically calculate the derivatives. Now, what are the derivatives? Derivatives are basically, for those, it's a very complex mathematical tool to calculate the gradient. Now, what is gradient? In layman term, I will just explain it to you. That's basically the slope. Okay, so, and what is slope? Slope is basically nothing but change in V1 for unit change in V2. Okay, so to explain it further, sorry. So we have this graph, okay? And we have this line which is cutting through the graph. So our x-axis, this is our y-axis. This is x1. This is x2. This is y1, y2. Right? So let's suppose the difference between x1 and x2 is 0.001. So for a very small change in the value of x, the change in the value of y is basically the gradient. Okay? So x2 minus x1 and y2 minus y1. So y2 and y2 minus y1, let's assume this to be 2. Okay, so for every unit change of 0.001 in x, y2 increases by 2 units. So 2 becomes a gradient, right? So it was just a small explanation of what is meant by gradient and what is meant by derivative. Okay. Yeah. So coming back to the topic. Yeah. So what we do in back propagation is basically calculate gradient. And once we calculate the gradients, after that, we adjust weights and bias. To reduce difference between prediction and ground truth. And there's a fancy name to it, which is loss. Loss based on y hat and y. Y hat is nothing but the prediction, and y is actual. So this is what we do in back propagation. So these two steps form the basis of this entire notebook. I will be running through this notebook. I will explain some of the things which I've done in this in brief. Okay, and I hope by the end of this explanation, you will have a good amount of understanding of how exactly a single neuron works, based on which we can basically move forward in forthcoming videos and create an entire neural network. Okay? So I'm just importing all the libraries. Yeah. I told you earlier that I've made this entire notebook in Google Colab. So what I've done is I've taken the data set and I've downloaded the data set on my local system and then uploaded the same on my Google Drive. Using Google Colab, I have accessed my Google Drive and mounted it into my Google Colab to access the entire data. And so that's the reason I have also imported the Drive library. H5 is imported because my data set is in the form of H5 file. Okay? And PIL is basically to play around with the image. We have Matplotlib and we have NumPy, which I have imported. I've also imported warnings because no one wants to see the warnings while they're working in on their project. Right. So the data set is publicly available. This data set, if you Google cat versus non-cat data set, you'll find this data set publicly available. There are images in this data set. Right? So this is how the entire structure of the data set looks like. We have train, we have test, we have images, and we have labels. And here also we have images, we have labels. And so this is Y, this is Y, this is X, this is X. So this becomes our train X. So I convert this into my train X and train Y. And I convert this into test X and test Y. So each of these images have this Y label. So these Y are labels. There are two classes, 1 and 0. 1 means it's a cat image, and 0 means it's a non-cat image. Okay, so this is the entire structure of how the data looks like. And you can Google this data. This data set is easily available online. So in this entire notebook, I'm not using Keras and TensorFlow for that matter, because normally Keras and TensorFlow is something which is being favored by everybody since they're easy and they're much faster, right? The libraries. But I'm not using TensorFlow and Keras because I wanted to show the intuition of the working of a single neuron. And so we use the typical Python codes in creating this notebook. This is how the data is. We have 209 images of 64 by 64 size. They are RGB because it's 3-channel. And our test set is 50 images of 64 by 64 size. So 64 by 64 is basically the pixels. So we have, what it means is, we have 64 pixels horizontally and 64 pixels vertically. So this is the square image. Okay, so 64 horizontal ones and 64 vertical ones, pixel. And there are 3 such layers of pixels. Right? So the first set represent R, which is red. Second set represents green, which is G. Third set represents blue. So, and there are 209 such images in our train set. And similarly, we have 50 such images in our test set. Right? Each of these images have their own label. So I hope I have been able to explain it. And each of these pixels will have one value into it, which defines the strength or the intensity of the color. Yeah, so we move on. This is how the labels look like, and this is how we interpret. So if it's a 0, that means the image corresponding to the first image in Y train is a non-cat. Second image in Y train is a non-cat. Third image in a Y train is a cat. So that's how we interpret them. So now I've just done a little bit of visualization to see how the images in our dataset actually look like. So this is a non-cat, which is 0. This is a non-cat, which is 0. This is a cat, which is 1. So this is how the labeling has been done. Now what we will do in our model is basically we will have one neuron. Just one moment. Yeah, so we will have one neuron. This image will be fed into this neuron. And this neuron will basically predict whether or not, or rather, it will learn to predict whether or not it's a cat based on certain parameters. The parameters are weight and bias, which I've explained earlier. right? So it learns. So once it's learned, there will be certain final weight and final bias, which will be generated based on which the uh, the final weight, the W final and B final, based on which the difference between our prediction and actual is least, right? So based on that, we create W final and B final. We then apply these W final and B final to identify the test images. So these are train and these are test images. So we apply these W final and B final on our test image. So that's how we make our model. Right. So before we create the model, there is some pre-processing that needs to be done. The most important of these pre-processing is basically the normalization of data. Now, these images, if we don't normalize, as I said, the pixel, these are basically 64 by 64 images, right? So there are 64 horizontal and 64 vertical pixels which are there in each of the images, right? So let's take an example: 10, 10, 20, 55, 175, 10, 11, 10, 15, 20, 10, 18, 19, 17, 15, 10. So this is a typical 4x4 image with pixel values. Each of these numbers basically represent the strength or the intensity of those, the color. So if we're talking about red channel, then these are the intensities. Now here, if you see 175 is an outlier, right? So this outlier is expected to affect my final results because it will give an undue weightage to this particular pixel, which I don't want. And hence, that's the reason we go for normalization of the images. Okay? So using normalization, we compress the images between 0 and 1. Okay? So none of these pixels basically get the undue weightage over others. Right? So that normalization is shown here. We've done a very simple normalization step. What we've done is we have divided it with the maximum value, right? The maximum value, the maximum value is basically 255. So a pixel can have a maximum of 255. If you see here, that's the maximum value and the minimum is 0. So the intensity of the color varies between 0 and 255. And after normalization, the intensity is shrunk between 0 and 1, right? In order to do this step, we also have to flatten. Before this, we have to flatten the image. By flattening, what I mean is each of those vertical matrices will be stacked on top of other, right? For example, this is how we can visualize this. If we have a 4x4 image, just a moment. So this is 4x4 image, right? So when we stack it, the first vertical stack comes here. Okay, then we have the second vertical step which comes here. And then we have the third vertical line, which gets stacked here. And then we have the fourth vertical line, which is getting stacked here. So this is what we are ending up with. So these 4 by 4 matrix will get converted to 4 into 4 by 1, which is equal to 16 by 1. So 1 is the number of columns and 16 is the number of rows. Okay. So that's what we have done here. Yeah. So that exactly is the reason as to why we have 122,088 data points in our train set, because our train set had 64 by 64 pixel images, which were converted to 64 into 64 is equal to 122,088. Okay, so these are the 12,288 data points. So 64 into 64 is equal to 12,288. So that's the logic behind it. And since we have 209 such examples, that's the reason we have 209 columns. So this is how it's shown, visualized. Just one moment. Yeah. So we have this column, which has 12,288 data points, which represents image 1. And then we have another column, which has 12,288 pixel values. This depicts image 2, right? And so on and so forth, 209 such columns. So this becomes our train data set. And similarly, we have our test data set, which has 50 columns of 12,288 pixel values. Yeah. So here we start the preparation of the model. So if you remember, I have informed at the beginning of this video that we have step 1, which is forward propagation, and we have step 2, which is backward propagation. If you remember, I've already explained what we do in all of those, a high-level explanation. However, I will explain it further now with how is it being implemented here in this notebook. Let me draw the diagram first. X1, X2 are the input data points, W1, W2 are the weights. Have the Y hat, the A, we have Z. So I'll again write those equations. Z is equal to Z1 is equal to dot product of W1 with X1 plus B1. Z2 is equal to W2 dot X2 plus B2. And A1 is equal to sigmoid of Z1. A2 is equal to sigmoid of Z2. Right? So this is F, the forward propagation, right? So these are the steps which are being done in forward propagation. Now, this is where we are calculating the Z train, right? So it's a dot product of weight and X. We have done a transpose of weight to match the shape. So matching the shapes is very critical. Otherwise, we'll end up with very weird looking errors in our code. So understanding of shapes is a must. I've not covered the understanding of the shapes here because it takes a little bit of time to get hold of the different shapes and how the shapes are changing. And so it's the same equation if you see wx plus b, that is equal to wx plus b. Right? Also, if you see, this resembles something very basic. Is nothing but y is equal to mx plus c. This is our linear regression equation, if you know about it. So if we stop the data processing at this stage, the first half of our neuron, what we end up with is nothing but a linear regression, right? Hence, to make it non-linear, we add in the second part, which is the activation. So this is basically the activation part. Yeah, so in this activation, I told you before that we'll be using sigmoid here. Sigmoid activation, if you see here, this is a sigmoid activation we've used. Although in practice, I'll repeat, we don't use sigmoid function that often, unless we are talking about binary classification. In binary classification also, in practice, we use sigmoid function only in the output layer, the final output layer. In between, we don't use, we try not to use sigmoid function. There are other functions which are available, which are much, much better than sigmoid. I will be explaining those functions in the upcoming videos. However, in this particular video for demonstration, and since understanding sigmoid is easy, we will use sigmoid function. This is how a sigmoid function is. So, once we calculate, once we calculate our z, z is equal to w dot x plus b, we apply a sigmoid on that, which makes it non-linear. Yeah. So what is sigmoid? This is the formula for sigmoid, to calculate the sigmoid. So 1 divided by 1 plus exponent of minus of z. So that's our sigmoid. So this formula basically converts the output, the z, the value of z. The value of z is continuous. So this formula basically converts the value of z between 0 and 1. Right? So a 0 means non-cat and a 1 means cat. And this is basically the probability of the image being either non-cat or a cat. 1 refers to 100% and 0 refers to 0%. Similarly, any value in between 0 and 1, for example, let's take an example of 0.65, will basically tell us that 65% of probability exists of the image being a cat. Okay? So, in short, what we are doing is we are giving a prediction which is nothing but the probability of y being 1 for a given value of x. Right? So this is what we are doing. In effect, this is what logistic regression is all about, right? So we have first applied linear regression followed by a logistic regression, right? And made the entire thing non-linear. This is one of the reasons as to why the neural network is also known as, sorry, a universal function, because here we are talking about a single universal function generator. Yeah. So what we are doing here in this particular video is basically understanding a single neuron. And I told you how complex it gets, right? So we are first calculating Z, which is linear regression. And then we calculate or we apply a sigmoid onto it, which is logistic regression. And we're talking about just one single neuron here. When we talk about a neural network, a typical neural network, this is how it will look like. We'll have the inputs coming in, going into the neurons. These are the neurons. And each input goes into each of the neurons. Right? And so on and so forth. So you see how complex the network gets. Now, post this, we have another layer of neurons. So all the neurons, sorry. So all the neurons output is being fed to all the neurons of the next layer, right? So again, there's a complex network, web-like structure, which is there. Okay? And then you have the output. You can have as many layers as you want here. And then you have the prediction. So it gets so complex that they are being termed as universal function generator. So they can create a custom function for anything. Okay. Okay. Right. So this is forward propagation. So initially, when we start, we in my notebook, I've started with initializing the values of W and B, which is the weights and bias, as zeros. Okay, so weights and bias are initialized as 0 in this case. However, in practice, that's not the right thing to do. In practice, we basically, we do the random initialization of weights and bias. It gives much better results and much faster convergence of gradient descent. Right? So here we have assumed it's a convex function. So this is how a convex function looks like, and this is how a non-convex function looks like. Right? So this is the gradient descent. Again, I'm not getting into the specifics of gradient descent. This is too complex a topic, which can be covered in this video. Okay. So based on this convex function, I have taken 0 as the initialization in this case. Okay. So yeah, this is what we have done in these 2 lines of code. Okay. Then once we have A is nothing but the y hat here in our case, right? So once we have the A, what we do is we basically compare A, which is nothing but y hat, with actual, right? So we compare prediction with actual. Right? So based on this, we calculate something called as cost. Cost is nothing, but as I told you earlier, it's a fancy way of saying the difference between actual and prediction, right? There is a specific formula to it. The mathematical formula is minus of 1 upon m multiplied by y times log of y hat plus 1 minus y times log of 1 minus y hat. Okay, so this is the loss function. Our aim is to reduce the loss function. This is how we also depict this at times. So this is our aim, to reduce the cost function. Sorry, the loss function, right? So in order to reduce the loss function, if we have let's say our prediction matches our ground truth. That means, so prediction is 1, ground truth is 1. So this formula basically, so when we put y is equal to 1 and y hat is equal to 1, this formula will become log of 1 plus 0, right? And log of 1 we know is 0. So total cost will become, sorry, the loss will become 0. So when the loss is 0, that means our initialization, or sorry, that means our W and D are ideal to give us the value of Z1 and Z2, which creates a value of A1 and A2, same as our ground truth. Otherwise, we need to change the value of weight and bias. Right? So based on this, we go back and do a back propagation. Coming over to back propagation. Yeah, so coming over to back propagation here. Backprop. Okay. So what we do is we do derivative. If you remember, I spoke about the slope of the line, which is nothing but the derivative, right? So we calculate the derivatives here. So derivative of z, derivative of weight, and derivative of bias. This is what we calculate now. If you have in-depth knowledge of derivatives, you will be able to calculate this and derive it. However, I'm not covering it in this video. I'll simply give the formulas for this. A minus y, which is nothing but the prediction. Let me put it this way. Yeah, sorry. So y hat minus y is derivative of z. Okay. So for a small unit change between prediction and actual, it will be this, it will give us the slope of z, right? Now derivative of w is 1 upon m times x dot product of dz transpose. You've done transpose so that it matches the shape of x, right? And bias is nothing but the average of sum of dz. So everything depends on this dz. Once we calculate this dz, dw and dv is easy, right? So if you remember, I told you, if the y hat is not equal to y, then that means we have loss. Then we calculate derivatives. Based on that, we update the value of new weight is equal to old weight minus alpha times dw. New bias is equal to old bias minus alpha time derivative of bias. Okay. Now these values of alpha, these are small values which we have already defined in the previous cell as 0.05. There can be multiple values which you can do here. Right? So you can do 0.01, 0.001, depending on what is needed out of this entire model, right? So based on our need, we can change it. So this is one of the hyperparameters which needs to be tuned. Since this is an easier database, data set, a 0.05 has worked very well for us. However, if it's a complex set of images, we might have to change it multiple times to arrive at the optimum learning rate, which gives us good results and lets the lets us converge the lets us converge the entire thing, right? So yeah, so this is how we update, and this is the one step that we are taking. So this is just one step, right? This forward propagation and this backward propagation put together is one step. Right? So in our case, in this notebook, I have done 700 such steps to get the final model. Right? Okay, so now I will match all these formulas to the code blocks, which will make it a little more easier. So this is the calculation of derivatives in this code block. Right? This is application of sigmoid function, which corresponds to here. And cost, I've already spoken about loss, I have removed it, but loss calculation is being done. Sorry. This is where we do the loss calculation and the updation of weights and bias. This is being done here. Right? So this is how it's being done in this entire code block. So with each and every iteration, we are getting a new set of weights and biases, which is moving us closer to predicting the y, which is the ground truth. And it is also reducing the difference between the loss, which is nothing but the difference between y hat and y, right? So logically, based on this, with each and every iteration, our accuracy should increase. Accuracy of the model should increase and our loss should decrease, right? So that is what is happening in this entire code block and model. Just one moment. Let me remove the entire scribble from here. Yeah. So if you see the last iteration on 700 iteration, our accuracy is 99.5%. Our cost is just 0.023%, right? 0.0233. So that is reduced with each and every iteration. If you see, if you notice, we have been reducing. The cost is reducing with each and every iteration, and the accuracy is increasing. If you see, there is a specific point beyond which the accuracy is not able to increase. Right? So that's yeah. So 662, yes. So on 662nd iteration, we got an accuracy of 99.52153110047847. And beyond this, we are not able to increase the accuracy further. What this implies is that our gradient descent has converged. Okay, so in this convex function of gradient descent, we have optimized the weights and bias to such an extent. Sorry. We have optimized our weights and bias to such an extent that our loss is the least. So this is what is being depicted here. And the same thing we can depict visually also in this graph. So if you see, there's a gradual increase in the accuracy. The red line is basically the accuracy, and there's a gradual decrease in the cost, which is nothing but the difference between prediction and actual. So there's a gradual decrease in that. So here is our, so we've been able to reach a 99.52% of accuracy on train set and 0.023 cost, right? The value of the weights is here. So these are the weights which if we use on any of the data set, are expected to give us a good result. So weights used to reach 99.52% accuracy. Okay. And this is the bias to achieve 99.62% accuracy. Sorry, 99.52% accuracy, right? So now we have the values of our weights and bias with us, which we can apply to an unseen data set. If you remember, there was a test set also, and this entire model has been trained only on train set. So we have got the values of weights and bias based on train set. Now we apply these weights and bias to our test set, which has not been shown yet. Okay? So we basically create Z test, right? Yeah. So we calculate the Z is equal to W dot X test plus B. And then we apply a sigmoid here, sigmoid of Z is equal to y pred, y hat, sorry. And then based on this, we calculate the cost. And then we create the prediction. And then we calculate the accuracy. So this entire application on test set is made using new weights and new bias. So based on this, we get an accuracy of 70%, which is decent enough, considering we have just used single layer and single neuron, right? So with a single layer and single neuron, it's so powerful that we are able to get a 70% accuracy. Just imagine when we talk about multiple neurons, say, let's take, only 4 neurons in 4 layers. So we have 16 neurons working together to get this, to create a function to predict whether an image is cat or not. So how powerful would that become? So now this is an example of overfit, where we have a lot of difference between the train and test. We can reduce it further while using other libraries, the libraries of Keras and TensorFlow. In this particular notebook, I have done that also using a convolutional layer. This is a Con 2D layer which I've used. And this is so easy. I mean, 1, 2, 3, 4, just 4 lines of code gets me these kind of results, which is, accuracy of 100% on training set and accuracy of 74% on test set. So it's so easy. However, we did not use it because I wanted to explain the intuition. And so I hope this video has been quite helpful in understanding how a single neuron works. My next video will be based on working of multiple neurons in a single layer and interaction between them. I hope I've been able to generate some interest from your end in neural networks, and I believe that you will watch my next video also. Thank you so much for watching my video, and have a good day. Bye-bye.